This video covers section 8.2, and in it we are going to first of all review how to solve linear inequalities. We did that a little bit before back in chapter 2, but then we're also going to talk about a new type of inequalities we can solve, and that's absolute value inequalities. And before we jump into any of that, we're going to look a little bit here at reviewing interval notation. You guys have used that before, but just to remember, the first thing is we always go from left to right on the number line. So if we have a graph solution, we want to start with the first thing that's shaded on the left and move to the right. If we have less than equal to or greater than equal to, we use brackets. So if it includes the value, we use brackets. And then if there's no equal to, if it's just less than or greater than, then we use parentheses. And then the last thing is we always use parentheses for infinity or negative infinity. One little reminder before we get started, and that is that when we multiply or divide by a negative, the orientation of the inequality sign switches direction. And we'll see that here in our very first example. So if you just want to make a little note of that in your notes. The very first example, when you're solving inequalities, it's just like solving an equation. You got to get the x by itself. So with that first example, if we want to get the x by itself, we would of course subtract 2 from both sides, which after we subtract 2 from both sides, that's going to give us negative 3x is less than 15. And of course then we divide by negative 3 on both sides. And here is where that little note we just made comes into play, because we divided by a negative, which gives us x. Now this orientation is going to switch. We're not going to use less anymore. We are now going to use greater than, and that's negative 5. If we were to graph this on a number line, we put negative 5 in here. This is going to be an open circle because we're not equal to, and it's going to be greater than negative 5. If I put that in interval notation, it's going to look like parentheses, negative 5, comma, remember we're going out to infinity here, so negative 5 to infinity. Final answer. Okay, hopefully that makes sense. Let's look at one that's a little bit more challenging, and that is that we have now fractions, and we've talked about this a little bit already in this course, but remember, when we have fractions, let's just get rid of them. Let's multiply everything by the least common denominator. So if I multiply this term by 5, then I have to multiply this term by 5, and I have to multiply this term by 5, I have to multiply this term by 5. I have to multiply everything by 5. The beauty in that is that these 5s here cancel. These 5s cancel. Our entire inequality becomes a whole lot nicer, because now we have 5 times negative 6, negative 30, is less than 3x plus 2 is less than negative 10. Now, this is what we call double inequality. We have to get the x by itself in the middle. In other words, we have to make it look like this example we did just a little while ago. Well, in order to do that, the very first thing I'm going to need to do is subtract 2. Now, if I subtract 2 there, I also have to subtract 2 here and here. That's going to give me negative 32. In the middle now, we only have 3x left because the 2's cancel. This is gone. And then on the outside, the other side, we have negative 12. Lastly, we want to divide both sides by 3 to get that x by itself. Divide all three sides by 3. The x's will cancel. We're left with negative 32 over 3. 3 does not go into 32 evenly. Is less than x is less than negative 4. If I go ahead and graph that on a number line, negative 32 over 3 is going to be roughly there. Negative 4 is going to be somewhere over here. We have open circles because there's no equal to, and we're going to shade between those 2 points. We're not going to include them, meaning that my interval notation is going to have parentheses, comma, negative 4, parentheses. Just the stuff that's between negative 32 over 3 and negative 4. Answers only fall within those range of values, the answers on the inequality. So that's a couple of examples. We have a basic linear inequality in one variable. We have a double inequality. Let's now look at another type of inequality called a compound inequality. That's when you have two inequalities combined together in a single problem. And really all we do is we solve each one separately and then look at what our answer is going to look like. So if I solve the one on the left first, my very first thing would be to subtract 4 from both sides, which gives us 3x is less than or equal to negative 21, which then if we divide both sides by 3, we get x is less than or equal to negative 7. You could also do the same thing on the other side. I want to add 9 to both sides. If I add 9 to both sides, I get 2x is greater than or equal to 16. And then I could divide both sides by 2, giving us x is greater than or equal to 8. Both of those parts are not real hard to come up with. I think everybody probably feels pretty comfortable about doing that. The difference with this problem is now we have two separate solution regions. We have a solution region on the left and we have a solution region on the right. Let's see what it looks like if we put both of those regions on the same number line. If I put negative 7 on here and 8 on here, the one on the left, the red one, is talking about this region with a closed circle because we are equal to negative 7 and everything to the left of that. If we're talking about the region on the right, that is again a closed circle because we're equal to, and this is going to include everything to the right of positive 8. So answers could fall either the red region or in the blue region. Now, in the same way, we could put each one of these solutions in interval notations. This solution is going to be everything from negative infinity to negative 7, including negative 7. And then the blue region is going to be everything from 8, including 8, with a bracket, out to positive infinity. And what we would say is that our answers can be included in both regions. And a lot of times what we do is we put this symbol here, which means union. It means the answer could be here or here. So let me box that answer up. Okay, now let's go ahead and move to a new type, the second main concept here, and that's the concept of absolute value inequalities. And I want to first actually state that there's really two cases here. There's case 1. Case 1 says that if we have the absolute value of x less than k, that inequality can really be rewritten as saying that x is between negative k and positive k. Second case we're going to talk about is what happens if the absolute value of x is greater than k. I'm going to suggest to you that this means that x is greater than k, or x is less than negative k. Note, either one of those cases, we've actually already solved a problem like that. We solved case 1 in example number 2. That was that double inequality problem we looked at. And then we solved case 2 in the last problem. That's when we had two inequalities. We called that a compound inequality. Now, what we're going to talk about, though, is why we can go from this absolute value form to these compound forms. And it all stems from the fact that absolute value means distance. It means distance. It means the distance from 0. And so I'm going to start off with a very basic example. And that is example 4 here. The absolute value of x is less than 3. What it's really saying is the distance has to be less than 3 away from 0. So I think the easiest way to think about this is to use a number line and say, okay, well, here's 0 right smack dab in the middle. And let's put the numbers -3 and, sorry, my phone just went off. Let's put -3 and +3 on this number line. And I'm going to kind of fence off. I'm going to put a little fence in here in red. And remember, what this means is the distance has to be less than 3 away from 0. In other words, we need to be regions that are inside. Our region needs to include values that are inside the yellow fence, not outside the fence. So our actual answer, we're not going to include 3 because that would be a distance equal to 3. We're not going to have a distance equal to 3, but a distance less than 3. So we're not going to actually include values on the fence, but we are going to include all the values inside the fence. So what I'm suggesting is then that this absolute value problem actually is case 1, which means that we have this double inequality that we talked about earlier. That means that our answer in this case is everything from -3 to +3. Now, what happens if it's the opposite? What if the absolute value of x is greater than 3? Well, it's still the same picture. We still have to talk about our fences being at -3 and +3. The difference, though, is that now we want to be a distance of greater than 3 away from 0. In other words, we don't want our answers don't include any values inside the fence. We are now going to include values outside the fence. So we're going to include all this stuff, which of course we've learned how to write that in interval notation. That would be -infinity to -3, and of course 3 to +infinity. And we would take the union of those two answers. Now, this is, as I just said, this is really case 2, isn't it? This is case 2. We just saw that when we have an absolute value greater than k, it can be rewritten as that answer or that answer. Okay, now they're not always this basic. They sometimes are a little bit more complicated. So let's take a look at two more complicated problems, which are really doing the same thing. The first one being this absolute value problem in question number 5. Now, one thing we always have to do in these problems is to isolate first. We need to isolate the absolute value. Oops. Isolate the absolute value first. So what I'm suggesting is that in this first problem we need to add 8 to both sides, which makes this look like the absolute value 4x plus 9 is less than or equal to 5. Now, that means that this is really an example of case 1. We have a less than, which means it's one of those double inequality ones. It's this stuff, the 4x plus 9, is less, it's between 5 and negative 5. Okay, now we already talked about how to solve something like this. We would first subtract 9 everywhere. Which means we have negative 14 is less than or equal to 4x is less than or equal to negative 4. And then we would, of course, divide everything by 4. This left-hand side reduces to negative 7 halves is less than or equal to x is less than or equal to negative 1. That, of course, is graphable on the number line as being everything between negative 7 halves and negative 1. Actually, I'm going to go ahead and do that in a different color so it shows up better. Which means our answer in this case is, in interval notation, negative 7 halves to negative 1. Okay, I hope that makes sense. Okay, so now let's take a look at example 6 here, and remember we first need to isolate, so this is going to be the absolute value of x plus 6 is greater than or equal to 3 because we subtract 5 first, and 8 minus 5 is 3. You'll notice this is now greater than or equal to absolute value inequality, which means we're in case 2, which if you'll remember from our picture we talked about earlier, case 2 is where our distance needs to be greater than that k away from 0, which means that our absolute value should look like greater than k or less than negative k, because we're in these blue regions over here. Our answers are in these blue regions. So what this means is that the x plus 6 should be greater than 3, or that x plus 6 should be less than or equal to negative 3. And again, we could solve both of these separately. If we subtract 6 from both sides, we get x is greater than or equal to negative 3, or x is less than or equal to negative 9. We could put both of these on the same number line. We have negative 9 and negative 3, and that would mean everything was less than or equal to, close circle, negative 9, or greater than or equal to, close circle, negative 3, or our solution set is negative infinity to negative 9, bracket, union, negative 3 to infinity. I hope that makes sense. The last example I want to look at is a special case, and that is example number 7 here, that says the absolute value of 5x plus 4 is greater than 6, than negative 6, excuse me. What that's really saying is that this absolute value, this distance, is greater than or equal to -6. Well, what do we know about distances? Distances are always positive. The absolute value of something is always positive. So this left-hand side is always positive. And when something that's always positive is stated to be greater than -6, that's a statement that is always true. It doesn't matter what I plug in for this x, -1,000,000, +2, 0, the left-hand side is always positive. And positive numbers are always bigger than negative ones, including -6, which means that our answer in this case is -infinity to infinity. It's all real numbers. It doesn't matter what x we plug in. It could be any x from -infinity to +infinity. We're always going to have a true answer. So I would go ahead and now work on these self-checks. If you haven't tried any of them yet, you might want to go ahead and start looking at them. They're all basically the problems that we talked about in the video. We'll see you in class. Thank you.